Let's welcome first Burla directly from Singapore, so from Basel originally. Yes. Let's go for the first 20 minutes.
Hello, thanks for joining this last part of the session. So, as I said, I'm working in Singapore and came here as community here for R is not very. There's not so much R communities in this area of the world, and I work for Singapore Lipidomics Incubator, which is a research program that is hosted or situated at the National University of Singapore. And this is somehow a PR slide from our lab, but yeah, so we are focusing on omics technologies and mainly metabolomics and lipidomics. So we're measuring lipids, hundreds or thousands of different lipids in mostly human samples at the moment. And so we do cohort studies where we measure a few to up to a few hundred lipids per sample. And this is just now some overview of what happened recently in the field. So these are more and more interest in these lipids and metabolites. And these are usually cohort studies with a few hundred samples to now it extends to 100,000, like the upper left publication is 100,000 samples. So we measure a lot of species, hundreds or even thousands of different lipids or metabolites, and in hundreds or 10,000s of samples. So that generates a lot of data. We have always the situation that in our lab, we have the analysts, the biochemists, and the analytical chemists that deal with this analysis, and then pass on to analyze the data. So this is the workflow here. We don't go to the technical details, but there's a quick overview. There's two processing steps involved. One is pre-processing, where the raw data from the instrument mass spectrometer is processed and gives them some kind of areas or quantitative data, initial quantitative data, and these needs then further be processed for batch effects, for drifts and quantifications and other corrections that we apply. And so we always have the situation that we have this biochemists or analytical chemists in our lab that analyze the samples and then get the peak areas with the first step, because there's a lot of software for this. But then they hand over the data to the bioinformatician. Bioinformatician then processes the data, and then this feedback loop until the data is processed or understood and goes back to the analyst takes a long time, and a lot of information gets lost. So often we have run analysis, and then only when it's too late, we know we should maybe adjust something in the analysis, then it's too late. So the biochemist somehow loses the control over his experiment by not being able to really analyze and look into the data in real time or in close real time. So we try to think, how can we improve this situation in the lab? And so first we look, of course, at available tools. And when you see in publication, when you read publication, you see always, for example, the R version is stated until every decade. But then what really has been done, the R scripts itself are rarely published. It's really amazing that there's a lot of technical details on the experiment, on which instrument was used until the last setting. But on the whole data processing, there's almost no information. So there's a few packages that have been developed. Some have been abandoned. But the problem with these packages is that they have limited functions, and they are programmed or made by informaticians or bioinformaticians, and a little bit meant for bioinformaticians too. So people from the lab, even they try to learn R, they are easily overwhelmed by these packages. And so they become black boxes for them. And they also, these packages, so these scripts that are available, they assume kind of perfect analysis, like analysis that have no issues, and also perfect data, structured, organized. And so what happens, people have to spend a lot of time to prepare the data, to go to Excel, copy paste different things, merge different things, leading to a lot of errors, spending time. And then maybe once in a while we have to realize there's something completely strange. Have to go back to the raw data, have to process, the whole thing starts again. It becomes often unreproducible. So the analytic reality is that projects are very different. As I said, we have 10 samples, 10 analytes, or thousands of analytes. We have different platforms, different methods that have different kind of data features. And sometimes the analytical runs, they go well, sometimes they fail, they have to be repeated, partially repeated. So mistakes happen, some QC samples are missing, some numbers, some dilution factors were confused, and so on. And so there's this the communication between the wet lab and the dry lab. Sometimes, especially when these kind of mistakes happen, they kind of stop. So it happens that information just gets lost. And then, yeah, so what we do. That's a little bit. Okay. So then just so a little bit the data that we have. So this metadata that the first is the data, of course, the raw data that I showed, that is processed by another software. And these data come from vendor software or from open source tools. And sometimes also we have generic formats that are of interest. The metadata is the big problem or the big issue. Metadata describes the samples, describes the futures that we measure, describes calibration curves. And then if you do a little bit exploratory data analysis, describes also the experimental groups and so on. And so these metadata, they exist in lab notebooks, in Excel sheets, in emails. And for data analysts, it takes along many emails, many communications to really collect all the metadata in the completeness that are valid, and integrity is correct. And often there's further steps. We realize that some of the metadata doesn't fit, or there's too many samples. Some futures don't have matching metadata, and so on. So we made some efforts. A colleague of mine has created Excel templates, macro-based, with all the disadvantages of macro-based Excel sheets. That forces the users, helps the users because it's Excel, so they're more familiar to provide the data, to import, for example, the instrument data and to extract some samples that have to be annotated. And then these tools can then be further on processed by scripts. And then now we also have started to use a lab information system, which is the only way to go if we really deal with large sample scales. So we have an enterprise-grade lab information system, SQL-based, where we then, this package I present, can access the data directly, some of the metadata, and hopefully more and more. So we try to come up with a package. So we had a long time, we had a lot of our scripts in our lab, and then we started to consolidate them. And the package should be not just for the data analysts, but also for the biochemical scientists in our lab. So they can take the data, they can prepare the metadata, maybe with, at the moment with this Excel or with the LIMS. We have entered the data in LIMS, it's available there, and they can at least get a first idea about it. So this is what I show on the right side here. So lab people analyze the data, they already get an idea if the analytical run has performed well, what are the issues, do they have to repeat something, do they have to adjust something? And then once they have done this, or maybe they have more questions, or they want to maybe do additional analysis, then they will share a project file, which I will describe later, to a data person in our lab. And then this person has a collection of all the metadata and data, plus the processing that has been applied, and can continue with this. And so the aim is really to have a kind of supervised automation. So we want, of course, especially when we have hundreds or thousands, 10,000s of samples and analyze, we want to automatize that. But we also don't want to apply data processing steps in a blind way. So we want to supervise, we want to see what the different steps do with the data. So that's why I call it supervised. And then it should be flexible enough to tailor for all these different packages, now for all these methods we have and requirements. And then it should be standardized, so that we have standardized formats of output, standardized reports, and it should be reproducible, of course. And the idea is really that you're able with this to share the data, but also to share the processes that are by which these data were prepared. And so the challenges are, they still have to learn R a little bit. We have a lot of effort in our lab, R sessions, R meetings, and it's really, people are just too busy, biochemists are too busy to really take the time, or they are not forced enough, especially when there's people around who still help. So that's one thing. Then the user acceptance of using R is still low, but sorry. And then it's always the different task is scripts versus user interfaces, programming shiny apps. We also tried, it takes a lot more resources, more skills, which we don't always have. And then if something doesn't work, then we still have to go back to R and install again. So that's the issues. But just saying a little bit what we did. So we created this package, and it's 4 classes that a little bit similar to bioconductor classes. Maybe also in future will be aligned more, try to align it more. So it creates an object that is a container for the data and processes. Then we load, for example, here the raw data. The first line is the raw data, and then the metadata. And then now we do a normalization step, and we then quantify. So that's a technical, but we just do a processing, and then basically we get concentration values like how many grams per milliliter plasma there were there, micrograms. And then we calculate the QC, the analytical QCs, and then we also can apply filters. So we can say reject everything that didn't have an analytical coefficient of variation be above 20% or something. So typical analytical chemistry parameters. And the idea is really that people can, the names are a little bit clear and well defined, so they can go through and can also copy paste such chunks. But then also that they get feedback, so that they really know what's going on. So often some of these packages, other packages I described, they will basically maybe give no answer, so you have to go back to the data and check. And so the idea is really to guide the user a little bit, and to also to inform the user what's happening, so that he has a feeling of what's going on. And this, I think, this kind of things helps a lot to get people to use it, because they feel something is working, and that's small successes can really help make life easier in a lab. And so we have this output at the moment in the console that really describes what's happening, and later I will also show cases where there's a warning or even error messages that come. Just another step is, so what we always have in this analysis, I will show you later, another example, the instrument changes sensitivity or performance, so we have shifts and everything, and we correct for this. So that's a big topic, and if you look at some packages, there's a lot of packages of this, but many of them just apply a standard transformation, a standard correction for this effect. And so we try to find a sweet spot in the parameters that we use. So we force the user to define some parameters, but we also leave some parameters modifiable but optional, so that they don't, if they don't understand it, they don't have to try and give some completely wrong answer. That's always big questions. And then here you see, here some error message or warnings. So the user says, okay, I'll do the Lewis smoothing because my samples were outside of the range covered by the QCs that we used for this smoothing. And also shows that some of the fits didn't work. So this kind of feedback is more and more implemented. And then just to see, so this is an analysis here of 5,000 samples in our lab. That took really total more than 6 months at the moment. Not great, but that's how it is. And the pure instrument time is 2 to 3 months. So an instrument is pumping solvents for 2 to 3 months just to analyze these 5,000 samples. Plus, in calling the study samples or the human samples are in gray, and then in red and green you have all the QC samples. And you see here, such plots can really help then the biochemist or the analytical chemist to identify issues that they have. So here you see in the zebra lines, you see the different batches, like the sample preparation batches, or here, for example, so for example, there was a preventive maintenance done, which didn't really prevent something, but actually caused a new artifact. And then columns were changed. And so by looking at this, we can, of course, qualify a process, so we can qualify an analysis, but we can also learn from it. And that's a big aspect. And the sooner these kind of analyses are done, the more easy the lab can adjust things and say, okay, maybe this preventive maintenance needs to be adjusted a little bit to make it really helpful for us. And so these are, then you see the diversity. And the thing is that we measure 1,000 samples or 10,000 samples, but we also measure hundreds of futures. So we need to come up with formats to really walk through this. One is to print PDFs. We also tried other aspects, and one way is to use kind of these HTML-based workflows that you can actually scroll through here. And so the user can then maybe also select, kind of pick the things that didn't pass some criteria and can look at it. So these kind of shareable analyses are more and more good. We still have problems with finding the best place to share these HTML files, but This is one step we are trying to do. And then also this, the package outputs, a little bit like before for GG survival, the output of this, some of the outputs are just basic plain ggplot files. And so here I have the output here of a function of the MidaR package. And then that can be converted into a plotly app with one command. So the user can modify the plots, or even maybe hand over to the bioinformatician, then he can continue to work on the data. He doesn't have to worry about metadata and everything. He can just focus on his real job to really create the visualization. So this kind of continuum between the lab people and the data scientist, and then at the end the statistician that really makes the real statistics, is a little bit the idea of this whole process. And then the last part is really on the sharing of data. So the whole process is tracked within the package, so you know what has been applied, and there's more details to it, like all the parameters that are used for smoothing, the Lewis bandwidth, or the CV criteria to filter something is all tracked and can be exported into a plain Excel notebook with different sheets. Can be passed on then to the statistician, or if we do fee for service, we can pass it on, like it creates reports directly. Another thing is we can save the object of MidaR directly as RDS, R object, serialized R object. And then by this, we can just send the whole R object to another person in the lab or to the data scientist, who then has all the data and the processing steps available, and just continue or modify. And let's say we have to reprocess, we realize we understand something better, we reprocess the data after 1 year, we can just take the object and reprocess it. And it's readable even without MidaR, you will be able to read the package. Yeah, and then, so that's a bit outlook. I mean, development of R packages. So I'm a chemist by my normal job. So this takes a bit, it's always challenging to really, as not data science focused team, to really produce such packages and to really also find a good spot with the lab, with the people in the lab to really make such a package successful and helpful. But it clearly shows now we also have really people who hate R because they simply cannot get used to it. They start now to really, they can see the data is processed, and they giving some plots, and they see the analysis went fine. Already makes them more motivated to even learn R. That's quite an interesting experience. That when they really use the data they use, instead of this penguins database, which they find cute in the first moment. But then what I often have experienced, they then basically stop because it's too abstract for them. It's too far away from their own work. So when they really see their own work, can get plots, then they will suddenly start to, oh, can I maybe modify this plot? And then you show them how, and then they will start to learn R themselves. So it was an interesting kind of indirect way to learn R. And yeah, so we also still open for collaboration and ideas, of course. And the next step will be then also to implement some parts of the user interface. And the slides are available on our GitHub. And yeah, thanks.
Very interesting to get buy-in from your customers in the end. That is what you are fighting with, yes. Right? Any questions from the audience right away? Yeah, please.
Very interesting talk. Are you also working on metabolic fluxes?
Okay. Oh, yes.
Yeah.
No, we don't do. No. So you mean if we do? No, we have not.
Yeah, if you're kind of having MidaR and then maybe just it for metabolic flux analysis.
Yeah. Yeah, we some of people start, yes.
Yeah.
Yes.
Okay.
It would be interesting. We look for different data sets also to include. Yes.
Yeah. Okay. Thanks.
Feel free to contact us or me.
Yeah.
If you have any ideas? Yeah.
So from my side, I had the question: how do you, so you obviously tried a couple of tricks to get the buy-in of your customers. What is your feeling? As first of all, it must be their data and not some abstract textbooks.
Yeah, that's one. That's message I got. Yes.
And more feedback, or what other factors make it important?
They really see the text of the command. They see normalize like this. That also helps them. And so the more language here it is, and anything that is technical like ggplot will already distract them. Yes. So we try to encapsulate a little bit the pain. I think once they start a little bit and they get the first plot, they suddenly start, okay, I can really do something.
If you had a server where you could place that as a shiny up,
Yeah,
would
that's
that help?
yeah, that would of course also help. The problem is then when yes, especially when we can then export the data into the app and then the data scientist, we just have a little bit of problem with the resources to really program that. But yeah, that's sure the next step we want to try. And then also the shiny apps. I mean, I have not much tried a little bit, but if you have 100,000 samples and or 10,000 samples and thousands of metabolites, seems a little bit slow to visualize.
Yeah, thank you for the interesting talk. Did you gain any experience on flow cytometry data analysis?
Well, we don't use this for, but we do also a few times we have done flow cytometry. Yes, yeah. Of course, this one is a little bit tailored to the small molecule analysis with the normalization and all. But you mean like quantitative or
Exactly.
Yeah. I mean, we don't do it, unfortunately, but always interested to hear new inputs. Yeah. Yes. Yeah. Okay. Good.
Thank you.
Thank you very much.
Thank you again.